Alright, today we are going to go ahead and continue with homework 1 for separations and get into part C. We will be first explaining and deriving the expressions to be solved in the determination of both bubble and dew pressures and temperatures for an ideal binary mixture. And then with these expressions, we are going to go into Python like usual and write some functions to calculate the bubble and dew temperature and pressures, along with the composition of the vapor-liquid phase. We're going to generate a few different diagrams and talk through that. Okay, I already explained this at the start, but we're going to go ahead and derive those expressions for the bubble and dew pressures and temperatures for an ideal binary mixture, and we'll go ahead and get started on that. So the first thing I would like to write down is Raoult's law, which I believe we've already talked about before, but if not, so right here we have this is the liquid mole fraction, and then we have the vapor mole fraction. We have two components. In this example, I believe it is toluene and benzene. And we know that the summation of the mole fractions in each of the phases should be equal to 1. So if we had 0.6 toluene, we should have 0.4 benzene. But that's just an example. We are going to start with the bubble pressure. And so we're going to start this by putting a summation on each side of the Raoult's law equation. And so what we can do after that is we can pull out the pressure, and this pressure is the bubble pressure. Since we are doing the bubble pressure, we know that the liquid composition must be given. And so what we can do here is say that this vapor summation, like we said up here, is equal to 1. And then we can take this and simplify it and say that the summation of this left-hand side is simply equal to the bubble pressure for this ideal binary mixture. This is our equation right here, but we can also, just to visualize it a little bit better, the summation would mean we are taking the liquid mole fraction of the first component times the saturation pressure of the first component and adding that to the same thing but with the second component. Now, like I said, toluene and benzene are our two components. Typically, component 1 is the more volatile component, which is benzene. So benzene has the lower boiling point and higher vapor pressure. We're going to call that component number 1, and toluene is component number 2. So we actually already have our bubble pressure formula right there, and next we want to do the dew pressure, so sticking with pressure. Sort of similar to how we started the previous calculation, we're going to put a summation on each side of the equation. And for the bubble pressure, we were given the liquid composition, and for dew pressure, we have to be given the vapor composition. So we're going to approximate that, well, not approximate, but as we said up here, use a different color. As I said here, this has to be equal to 1. And this is our dew pressure. And when I say bubble pressure and dew pressure, what that means is for the bubble pressure, that is the pressure at which the first bubble forms in the liquid portion, and the dew pressure is the pressure at which a droplet first forms in the vapor section of this mixture. We then have Pi, the saturation pressure, equal to the summation of Yi. The pressure actually comes out of there, so. And then we see that the dew pressure is equal to the summation of the saturation pressure divided by the vapor mole fraction. Once again, this is our equation right here. And to visualize it better, we could write it like this. Since we have two components. Next, we're going to talk about the bubble / dew temperatures. We don't exactly, unlike the pressure, the bubble pressure and dew pressure, we don't really have an equation that can just straight up solve for these. So instead, and this is part of a reason for doing some code, but in the code we are going to find what temperature will give us either the bubble pressure or the dew pressure. So the temperature that gives us the bubble pressure, that will be the bubble temperature, and the temperature that gives us the dew pressure, that will be our dew temperature. So there's not really a great way to solve that, but that's okay because we have equations that can solve for the bubble and dew pressures, and using those answers, we will be able to find the bubble and dew temperatures. Alternatively, if you have a graph, you can just look at the graph and figure out where the dew or bubble temperatures are. So let me grab my graphs that I drew out really quick. I went ahead and I drew a couple diagrams. So on the left I have the PXY diagram. This shows how either the liquid or vapor mole fraction of the first component changes with pressure. So that's at a constant temperature, and the TXY diagram is at a constant pressure. Here we have a bubble curve up top and a dew curve at the bottom. And if we were given an x1 here, we would simply follow this up and over, and where it intersects with the dew curve, that's how we get our Y1. And also, this right here would be our P, our bubble pressure that intersects with the bubble curve right here. And we also have the dew pressure right there. And over here, if we had the next one there, you follow the X until it reaches the bubble curve, because this is liquid. So right here, across to here, and down to get our vapor mole fraction. And again, we have the bubble temperature there. And if you keep going up, then you get the dew temperature. So I'm going to go ahead and get into the code now. Now we'll get started with the code, as I was saying. So like in my other codes, I just imported this from my class GitHub. It just has some other imports in it, and then it also has some functions and calculations for us to pull from rather than type out every time we would like to use them. And what we are going to do first is write those functions for calculating the bubble and dew temperatures and pressures. So first, I want to get started with something that can pull the data from this import. So this will pull, if I type it out correctly, benzene and toluene from the imports. We listed benzene first because, as I said earlier, benzene is the more volatile component, and traditionally you would put that first on there. And so we will first do our bubble pressure, because that is the one that we calculated first when I was writing that out. So as we know, we're given the liquid mole fraction, and we have a temperature corresponding to this bubble pressure right there. Our next step is once again pulling from the import. We want to get the vaporization pressure, or the saturation pressure of each of these components, given a temperature. And from our equation earlier, we had Yp is equal to X times vaporization pressure, and then we also know that the total pressure should be the sum of all of those partial pressures, and we will want to return the pressure and the Yp over P. So this Yp over P, that gives us the vapor mole fraction. And next we can do the dew pressure. As I said when I was deriving these equations, the dew pressure, we have to be given the vapor mole fraction, so that Y right there, and I meant to type a T there. So to find any of the pressures, we need to have some sort of temperature in our variables. So again, I'm going to pull from the imports to get our vaporization pressure and our vapor pressure. And we calculated that P should be equal to the summation of the vaporization pressure times the vapor pressure times the vapor mole fraction. I don't know why I keep saying vaporization pressure, I mean vapor pressure. And this should be the vapor pressure divided by the vapor mole fraction right there. And we would like to return pressure, which that would be the dew pressure, and Y times pressure divided by the vapor pressure should give us the liquid mole fraction. Next, we will do the bubble temperature. As we said earlier, we need to be given the liquid mole fraction for that one, and to get a temperature, we're going to need to have a pressure in the first place, so that's our other argument right there. And let's see, I don't think we need to do that again. We're going to say that so what we want to do here is start with a guess for what the bubble temperature could possibly be, because we don't have an equation to directly solve for this. So what I'm going to do here is do a weighted average of the boiling points of each of the pure components at the pressure, at this pressure P right here. For benzene and toluene, which that is in the imports right there. So that would be a sum of X times the boiling point at the given pressure and let me just run this to see if I have any errors. Yeah, I think I just totally did not put any of those there, any of those colons there, so let me add those. Okay, so I didn't run into any errors, so I think we're good to move on. And what we're going to do now is we want to be able to find a more accurate temperature that describes the bubble temperature, which is the temperature at which we achieve the bubble pressure, which is also when the first bubble or gas bubble vapor forms within the liquid fraction. So to do this, we are going to define another function within this function. I'm going to call it find T, so find the temperature. It's an argument of the temperature, and we are going to return the bubble pressure at the X and T temperature values given, starting there, subtract from the actual, not the actual, this would subtract from the pressure calculated here. And this difference, we want to be able to make that as small as possible. So we are going to do an optimization of this find T function at here. Our method is going to be secant. We want the root of that, so that gives us the answer. And we would like to return this temperature, and then this will give us the vapor composition. Let's run this and see if we have any errors or anything. It looks like it's all right. So I'm going to move on to the due temperature. We have the Y and P. We want to have a starting point similar to how we did the bubble temperature. Like we did above, I'm going to just label this the same way, find T, so find the temperature, and return the due pressure. Yeah, that should be correct. So we want to minimize this like we said earlier, and the temperature that we are going to use is we would like to optimize our find T function at x0 equals the temperature, the first temperature, and we'll use that same method right there. I'm going to run this and see what it looks like, and it looks like it's good. So we wrote the Python functions for the bubble and due temperatures and pressures, along with the composition, which was the second value right there, and all of these functions. And rather than test these functions individually, I'm going to move on to the third part to generate the binary VLE diagram for this ideal mixture. So we're going to be doing this at a temperature of 360 Kelvin. So this is our PXY diagram because we have a constant temperature. So we're going to set our temperature to 360 degrees Kelvin, and we want our x1s on the x-axis. So we're going to do linear space. We're going to have 21 points along this axis. We're going to have, for now, an empty vector for the pressures and the vapor fractions. For each x value in our x1s list, for this we are going to pull from our bubble P function, which had the pressure and the vapor fraction in there. So we will be doing that. This is equal to bubble P array, and we're going to have the x1 value and 1 minus x1. So right here, this would be the benzene liquid mole fraction. This would be the toluene liquid mole fraction. And the temperature. We want to add this pressure into our empty P vector so that we can graph everything later on. And we want to do the same thing with the Y values. So taking that vapor fraction, adding it to our empty vector up there. I don't want to do this, so I'm going to get rid of that. And what we're going to do now is prepare our plot. So make subplots from Plotly. We're going to add scatter. So we've added the scatter. The x-axis is those x1s. The y-axis is the p's, since this is a pxy diagram. And let's see. I want to call this the bubble point. And then we can add another scatter where the x equals y1s The y is still the pressures, and the name of this one, since we are using the y1s, which is the vapor composition, this gives us the dew point curve for the vapor. I want to update the layout, so giving it a title. Let's see, I'm going to call it the PXY diagram. It's isothermal at 360 degrees Kelvin. I want to title the x-axis as the benzene mole fraction. I'm going to give the y-axis title pressure, and this is in pascals. And then I'm just going to set a width and a length. And see if that gives us something. And this totally should be height. I did width, and now I should do height. There we go. I'm also going to change the appearance so that it's a little easier to read. And let's make this a little bit wider. And see what that looks like. Okay, so we have our PXY diagram at a constant temperature. This is our bubble point curve, and this is our dew point curve. And it looks pretty good. So like I was saying earlier, if we were given a liquid mole fraction for benzene of 0.2, we would follow this up the y-axis until we hit this bubble point curve, go to the right, and then get the vapor mole fraction as well. So I do think that my graph is a little bit big, but that was good for showing it. I'm going to make it smaller so that we can continue. Oh, that's very small. That's okay. It can stay small. And now I believe we need to do our TXY diagram. So the TXY diagram is at a constant pressure of 1 bar. So we have 1 bar. We are doing TXY diagram. So I'm actually going to copy and paste the PXY diagram code, and I'll just change this like where I need to. So this has a set pressure, which is 1 bar. 1 bar is this many pascals, so there we go. We'll do the same thing with our x1s, and we, instead of creating an empty vector for the pressures, we're doing that for the temperatures, and the same thing with the y's. So for x1 and x1s, we are doing ty, and we're going to use the bubble temperature, which up here we needed to supply the x and the p. So the bubble temperature, we have x and we have p right there. We want to add the temperature that it calculates, add the vapor fraction, and then we are going to make the plots. The y is using the temperatures, and let's see. This should be right, this is right, Still, we are doing a TXY diagram, isobaric at 1 bar. Temperature is the y-axis. This is in Kelvin. And I'm going to make this bigger so we can look at it, and then I'll probably make it smaller like I did previously. Okay, I found where I went wrong. So with I was pulling this bubble temperature, and up here, instead of doing dot root, I did dot root scalar, which was not giving me any real values. So just getting rid of that. Dot root should be good. And here is our TXY graph, isobaric at 1 bar. I'm going to go ahead and make this the same size as I made the other one, just so I can get some more space. So we got our tiny little graph right there. And let's see what's next. So now we want to write a Python code to generate an XY diagram at a constant pressure. So what we're going to do here is we'll actually have the liquid composition and the vapor composition on their own axis, and then we'll be able to compare it like that. So again, we're making the subplots, and we would like to add a scatter with, again, the x is x1s, sorry, x should be x equals x1s, the y equals y1s, the mode is going to be, we'll do markers for this one, and we're going to call this the actual data. So this is what our actual data is. And we would like to compare this to a 45-degree reference line, which I will make next. So that's going from x equals 0 up until 1, and we also want to do that for y. So we have that same thing here. And we'll have this be a line, and I'm going to give it a line color and give it a name. And we can update the layout again. I'm actually going to go ahead and copy this again, because it has all the things that I want to put in. So I can just change the title and everything. We're going to call this the XY equilibrium diagram, which is the McCabe-Thiele, using the McCabe-Thiele calculation. The x-axis is the liquid mole fraction. The y-axis is the vapor mole fraction. And again, I'll make this bigger so we can kind of see what's going on a little bit better. So what this shows us is if these were in equilibrium, meaning the liquid mole fraction at any point would equal the vapor mole fraction. That's what this line is right here, this like brownish line. And then this is our actual data. So this happens because benzene is more volatile than toluene, so they're not going to have a constant relative volatility. They're not going to have a linear line. They're going to have some sort of curve like this. See here, we made sure to explain and derive the expressions to be solved in the determination of bubble and dew pressures and temperatures for an ideal binary mixture. We also wrote the Python functions to calculate the bubble and dew temperature and pressures, along with the liquid and vapor phase compositions. The VLE diagrams, we did a PXY diagram and a TXY diagram, and those looked pretty good. And we also wrote a code to generate the XY diagram for benzene and toluene at the constant pressure of 1 bar. You can use any one of these graphs to physically find values, and you could also go ahead and use this code here and give it these arguments, and it'll return the pressure and mole fraction. So I'll do that right here, just for an example. So we'll write that there. Let's do 0.5 since that's easy to see on my small graph. And the temperature we would like to do is 360 Kelvin. That's the best way for me to compare it to this graph to see how it did. And so it looks like we're sitting at 86,000 roughly for our bubble pressure. So that's looking pretty accurate right there. I was showing us earlier, when you get to that bubble pressure and you go to the right, let me see if I can do this a little bit. I'll just make this bigger. So we had a mole fraction 0.5 for our little test, and the bubble pressure was about 86,400, so that's that point right here. It even has it labeled, that is the bubble point for that mole fraction. And if you follow this to the right, you get the corresponding vapor mole fraction for benzene, which is about 0.72. That gives it to us right here in this array, and the 0.28 is the toluene vapor mole fraction. So that tests the function. And again, you could do that with the dew pressure, bubble temperature, dew temperature for any of these graphs. And that is it for part C. Part D will be the last part for homework 1, separations, and in that we're going to dive into constant volatility and see how that describes the benzene and toluene mixture that we coded today. So stay tuned for that.